Hello, everyone. Welcome. Thanks for joining us. If you're a return guest, it's great to have you here. Or if you're new to the stream, it's good to have you here. Looks like we do have a couple new folks in the chat. So hello. Welcome. How's everybody doing? Hope no one is in too snowy of a place. For whatever reason, we managed to avoid all the snow here in Pittsburgh, which is not to say that it's not still cold and miserable. Well, if you're snowed in, nothing better to do than do a little bit of coding, especially tonight's stream. It's one of my favorite things to teach ever. My mom sent her regards. This is the first stream she's not been able to attend. So she's a minor celebrity within our chat. But she's not going to be able to make it tonight. Sadly, she has her card group, so she's playing cards this Monday evening. And she'll be back on Wednesday, so don't worry too much about everybody's favorite person. So she'll be back on Wednesday for our part 1 finale. She is, as the chat very quickly gleaned, she's really a very kind and generous person. And I say that as a preliminary statement to the fact that playing cards with her is something that I would wish upon no one, because she is first and foremost good, but secondly, she doesn't think that she's good. She's also one of these card players who will constantly complain about the cards that she has as she's playing the game and make comments about it. And say, I don't know what I'm doing. These are just not any good. And then she'll get another card and say, and put it in the hand and so on. And then like 3 turns later, she'll just be like, oh, I won. Yeah, I'm out. Yeah, sorry about that. And we'll just be saying, what on earth were you doing there? You commentated that hand as if it was the worst thing that had happened in human history. And here you are winning again. Couple short announcements before we start. Did I say Wednesday's stream? Yeah, Thursday. Normal schedule. Thank you for listening closely to my rambling. 2 big pieces of news. The first is the main piece of news. Our ebook is out. So if you're on our mailing list, if you're not on our mailing list, make sure to join. We've got a link in the description. If you're on our mailing list, you'll have gotten a message from me with information about our ebook. And we posted links to it in the pinned message here. So there's 2 ways to get it. We posted it to Gumroad. We also posted it to LeanPub. But there's a promo code that we have set up on Gumroad so you can get the book. It has preview material of part 2. So I went ahead and added 2 chapters of material for core text for part 2 of the course. So there's chapters on building a gravity simulator and simulating the 3-body problem. And then there is text on building evolutionary trees. And both of these topics are going to depend on object-oriented programming, which is something we've had a little flavor of, but it's something that we're really going to start heavily when we move into part 2 of the class. You also can get the book just by becoming a Philomath member, and we include that with membership. The next message we're going to put out is, if you've enjoyed the class, I hope you have, you'll get a certificate of completion by going through Cognitera and completing all the autograders, or a good number of the autograders. If you're interested in taking the steps beyond that, we're putting together like a capstone project of sorts. And so we'll have a menu of options that you can pick from with opportunities to get feedback on what you're doing and build something that's just a little bit beyond what we're doing here. So hopefully I'll see you in part 2 of the course anyway. But that'll give you an opportunity for the next few weeks to sort of reinforce everything that we're doing here if you want to take that deeper dive. And that'll also be a member benefit as well. Then we won't be having a stream next week because we're going to have a little opportunity to recharge. It's our spring break at Carnegie Mellon, so it'll be a little opportunity to recharge, and then we'll start part 2 the following week. All right. So for tonight's stream, you're going to need some starter code. And I put the link to the starter code in the description of the video, but we're going to go ahead and post that also in the chat so you can get that zip. And then all you need to do is unzip the file, or the folder I should say, and place it in your Python src source code directory. So you're going to get a Game of Life folder, and it's going to go here, which is what I have here on the screen. It's got a lot of folders and a lot of files on it, which is exciting because this represents our ability to make a transition towards solving some more, building some more complicated projects. And this is what we're going to do next time, where tonight I'm going to implement Game of Life. The next time we're together, we're going to extend what we do to build something that will simulate all cellular automata, including self-replicating cellular automata. But we're going to be able to implement literally like any of a main category of two-dimensional cellular automata. And there's like trillions of these, or infinitely many, I guess, if you allow for as many states as you like. So we will see that next time. Today's theme is all about taking the starter code that we have and building out the Game of Life. It's often called Conway's Game of Life because it's attributed to John Conway, who helped really popularize this. And it's become the cellular automaton that most people who know about automata are familiar with. It's not my favorite necessarily, although I think it's really cool. My favorite you'll see as part of what we do next time on Thursday. But it's a great automaton to build as an initial project. So that's what we're going to do. And last time we drew this thing, so we know what it's going to look like. And this time we're going to build out the engine behind actually implementing the rules of this system and then visualizing it over multiple generations. All right. I'm letting my cough drop settle in because somehow I still don't have my voice back. But I think we're ready to start. I'm going to build cellular automata, starting with Game of Life, and let's code. So, to get started, you're going to have a Game of Life folder that comes from our starter code that's in your Python src directory. It's got a number of different components to it that I want to walk you through. And first and foremost, I'll point you to the boards folder. The images folder is something you're probably not going to have. It's just something that's on my end so I can show you images as we go. So you'll have everything else. And the boards folder is going to contain CSV files corresponding to initial states of Game of Life automata. We have an images folder that, as I said, you're not going to have. An output folder where the things that we draw are going to go. And then we've got a bunch of Python files. So output folder is empty currently. The animate file is going to contain code for animating and like rendering a video of the Game of Life, which is what we want to see. We want to see this thing over multiple generations. And we're also going to have a custom IO file. This is where we're going to have code to read from a file. So when I have these boards that are stored, these initial states of this automaton that are stored in these files, I want to be able to read in these automata and store them as a list. Datatypes.py I'm going to talk about here momentarily. This will contain types that we declare. It's currently going to be empty. No, it's not empty, but it's close to empty, and I'll explain what's in there. Main.py is where I'm going to have code for running the simulation. So it's probably close to blank. In functions.py, we'll have a bunch of functions that appear to be written, but they're not. I've taken it upon myself to write out the doc strings for us and do some error checking with our parameters. Not because it's not important, but because our work here is already pretty sophisticated and will take us some time to get through. And so I will point you to these doc strings and this error checking, but it's not something that we're going to do so much right now. Now, where should I start? Let's start with data types. And when we've worked with the game of life before, we know that we think about a game of life board as a two-dimensional list, and that two-dimensional list contains Boolean values. So it is represented as a list of lists of bools. So it's like a one-dimensional list where the values in the list are themselves lists. But we always think about that as a two-dimensional list of bools. Here's my opportunity for the first question for you, which is our highest level function that we're going to write is going to simulate multiple generations of a game of life board. So it needs to start off, it needs to have as an input a game of life board, as well as the number of generations that we want to run this for. But what we want to return is what? What is it that this function at the highest level of our engine for the game of life, what is it that it should return as a result of producing this simulation? A little bit of disagreement in the chat, but the good news is that you're all right. So we have some folks who are saying, on the one hand, we could return a list of boards. On the other hand, we need a three-dimensional list of Boolean values. And the good news is that both of those answers are correct. So I want to think about what's happening as, well, remember, a board is a two-dimensional list of Booleans. And that means a bunch of boards, the natural way of storing them over a collection of generations, would be as a list. So we would have a list of two-dimensional list of Booleans, which means that I have a three-dimensional list, which is a list of lists of lists of bools. And I want to be able to frame it that way. It's important. However, conceptually and abstractly, and here is our slight movement towards thinking about object-oriented programming. I want to think about a board as just a board. And then our function for simulating the game of life is going to return a list of boards, a one-dimensional list of boards. One board corresponding to each generation that we're going to simulate. So that is a little brief peek at abstraction, and I will say more about this. But in the meantime, datatypes.py is going to declare a game board as equal to a list of bools, or a two-dimensional list of bools. So in Python, this is called an alias. It means that anytime I wanted to use a two-dimensional list of Booleans, I can also just use the term game board instead. So this is to help humans as much as anything else, because behind the scenes, the programming language is going to appreciate that if I have a list of these things, I've got a three-dimensional list of bools. But it's going to make our code a lot cleaner and easier for us to understand, because we're conceptualizing a game board as this two-dimensional list of bools, especially, again, as we move towards a list of these game boards and not having to think about it as a three-dimensional list, which is also just going to be a little bit ugly to type out. So it's a little bit beyond, John had a question, is it Is it just for type hint purposes? I'd say it's a little beyond that, because this is a powerful idea that I'm abstracting one thing as naming it another thing. And I think we can go beyond this in terms of aliases for Python. It's not going to be what we do now, but I introduce it because I truly want you to think about a game board as an object. It's just that that object is something that we're already familiar with, which is a two-dimensional list of bools. And if you think about it as both of these things, the simpler thing as well as a conceptualization of it, which is an object, that's going to be very profitable, especially as we move towards object-oriented programming. Now, that's all I want to say about datatypes.py, because it's a brief glimpse at this way of thinking, and that's all it's going to be. Everything else is going to use the types of stuff that we're familiar with. So we don't need any other special data types. The next thing I want to do, though, is read a board from a file. And we've looked at parsing before, and we know parsing is unbelievably boring, and I want to spend a limited amount of time doing it. But I also think it has some features that are worth profiling because they connect to the sorts of things that we do elsewhere in the course. And so since that's the case, let's write read board from file. And let's look at, actually, before we even get that far, let me, for example, look at our boards. We can't know how to read our data until we look at the boards. So here are 3 game of life initial states of automata. Probably the easiest one to take a look at is this dinner table automaton, because it doesn't have a bunch of values on each line. So it just has 15 lines here. It's a 15 by 15 grid. And we can immediately, I think, see how this file is representing a given game of life board. We know that the values have to be either alive or dead. And I'll tell you now, the ones are alive and the 0 values are dead. So each row consists of a single collection of 0s and 1s that are separated by commas. That's why this is a CSV, or a comma-separated value file. And then our goal is to read this out line by line and convert all this information into a game board, which we know of as a two-dimensional list of bools. We're eventually going to draw these and render them. So I'll just show you, these are our friends. The dinner table produces this pattern. So this is, I think, a period 12 oscillator. And spoiler alert, we have the pentomino that produces this pattern from just 5 alive cells at the beginning, and then goes on to greatness. So I don't want to spoil the rest of it if you haven't seen it. Then we have a glider gun, which produces these glider 5-cell elements that seem like they're swimming off into infinity. I want you to remember that when we drew the boards, we drew them in a slightly different way. And a lot of the folks in the chat at that point in time wanted me to add grid lines. And I want you to take a look at these. And a couple of them are not the highest resolution, but I want you to look at these, and especially the larger ones. And to me, the grid lines are just pretty intrusive, because I'm not going to be zooming in and saying, oh, what's going on at row 7, column 23. That's not something that is of interest. I'm just trying to make a pretty visualization. So remember how these look like, and then hold on to that thought, because when we implement this later, I think our visualization is going to be a lot prettier, and that's going to prepare us for general automata, as well as some of the things that we'll do in part 2 of the class, where this same line of thinking is actually going to come back when we talk about parallel programming. You're going to do some practice exercises that get to use this visualization. And they're pretty neat, because we took the time to make a pretty visualization now, and it'll pay dividends in the future. For now, what I want to do is I want to write this function that will read the board from the file. So how do I access a file? Just need a string. And it'll produce a game board, meaning a two-dimensional list of booleans. So if I go to customio.py, I've got this function, read board from file, takes my string, produces a game board. And I've got just a stub and some value checking there that we automatically added. First thing I'm going to do is I need to make sure, and I've simplified things a little bit for us here. I need to make sure that I have the game board type. So a lot of times you'll see this line. If you use a function from another file in the same folder or from a module, then you need to import it. And the same is true for any types you declare. So it might be seemingly attractive to put all of your code into one file. It will be so much cleaner if we divide things out by task. And then remember that we're going to need statements like this because I'm going to need to access a game board, so I need to import it from datatypes.py. All right. So we've started working with how to open a file. And when we open the file, we can say open, file name, and we want to give it R to indicate that we're reading from this file instead of writing. And I want to say the object that is going to be produced is going to be a file object that I'm going to name F. So file object, we'll just use a simple single letter variable name for it called F. I'm going to add one initial word to this called with. So when you have code that looks like this, all it's doing is opening the file name, or the file given with this given name. We're opening it in read mode, so I'm going to be able to read in from the file. And then I'm naming the file object that Python is going to give us as F. The with statement is just a simple initial comment here, or initial keyword, that's going to automatically close the file as soon as this block ends. Okay, so with means close the file at the end of the block. And because that's the case, I need to do all the file processing inside of this block. It turns out I don't need to do much. The only thing that I'm going to do is call a function called f.read. What that does is it goes into the file, reads out the entire thing, and the whole file winds up getting read in as one giant string. So if I really want to express that I understand what's going on, I'm going to name the result of reading the file giant string. And then what's nice about it is the file has served its purpose, because at this point in time, I have everything in that giant string that I want to work with. Then it's just a matter of processing it, because I think, well, it's got all of these values in it that we had before. And then it's got a lot of like new line characters, but I'm representing this entire string now. So with that being said, I need to then process the string. And the first thing that I want to do is I don't want to have my code broken because somebody does something like this or adds a new line. Okay, so for that reason, I will trim any leading or trailing white space. And we're going to work with giant string. So as I said before, F has served its purpose, it's through. But we read it all in and we got the entire file content. So I don't need F anymore, but I'm going to work with giant string. And I'm going to have something called trim string, which is called, and I'm going to call giant string dot strip. So the dot strip function just removes any white space that might occur at the start or the end of the file. Then I've got a huge string, and I want to chop the string up into its constituent, that's a fancy word, lines. So I'm going to write a function called trimmed string dot split lines. I'm going to call that function, excuse me. And as a result of that, I will get a list of strings. So now each element in a line is a string corresponding to one line of the file. Okay, so we're starting to be able to work with the board, which is what we want. We want to read in this information. We've got all the information, we need to parse it. And then I want to add the values to board. So let's go ahead and declare my board. And we're declaring, we've seen how to declare an empty list before. In this particular case, instead of needing to tell it, well, board is a list of bools, we might have done this before, and then to say it starts as an empty list, I can just say game board. Here's our first opportunity to use that alias to just say I'm declaring a game board and it's going to be an empty list. So it starts off as empty, and now range over the lines and parse each one. So as I said, each element in lines is a string. Each string corresponds to one line. And so I'll say, well, let's range over those. And current line is going to represent the initial line, or the current line that I'm working with. And when I do that, I'm going to say, okay, well, I've got a file here where in the current line, the elements that I care about are all separated by commas. So I might have a string right now that's just this. So I need to split this string where I'm paying attention to the splits need to occur at the commas. So I'm going to throw out the commas. And so if I come back to custom IO, what I want to do is to say I'm processing current line. So line elements is equal to current line dot split, and we're going to split this current line at the comma, and this is going to give us a list of strings as a result. So line elements is a list of strings now. It's important to think about because we look at this dinner table example. That means that now we've got a list. We've gotten rid of the commas, but the list is the string 0, the string 0, the string 0, and so forth. Sometimes we have the string 1, but we don't have the integer 1. So we still have a bunch of strings, one corresponding to each value. And here is where I'm going to say, well, we need to now parse the row. And my question is, what is this starting to smell like? What does this smell like? Good, Lori, smooth sailor. Good, like that. It feels like a subroutine would be useful. If you have other thoughts, and this goes back to some of my previous thoughts about Python, but can all this be done with like a list comprehension? Yes. Is it hideous? Yes. Are the Python people going to defend it to the death? Also, yes. But in this particular case, I'm going to write it in a way that's a little more, maybe less Pythonic, a little more language neutral, and a little bit more, I think, intuitive, which is, if you ask me to parse a bunch of lines, I'm going to range over the lines and parse each one. And so that's where having this just as a subroutine is often really natural to think about. And so we can say new row is equal to set row values. And in this particular case, I've got a set row values that takes a list of strings, and it's going to also take, it's just going to take my list of strings, excuse me, and it's going to return a list of booleans. So it's going to basically just go through and convert all of the strings that we have, which are zeros and ones, into boolean values, and that's the row that we care about. And once I've got that row, then I can just append it to board. And once I've got the board, then I can return it. I will go ahead and write set row values because I think it's a simple function. After we have made sure that the values are appropriate, all we want to do is range over the elements in this list and convert them. So we have line elements, which is a list of strings corresponding to 0 and 1 strings. And so I know I've got a one-dimensional list of strings. I just need to range over all of the values in this. And once I'm at the current value, I'm just going to say if it's equal to 0, well, take the current row, which I haven't declared and I probably should, and append to it the value of false. So what is current row? It's an empty list that we started with. Okay, and it's a list of booleans. So I could declare it in this way. Else if value is equal to 1, and it's the string 1, as this is the string 0, so I should be careful there. And if it's the string 1, then that's a true value, so current row dot append the value true. And then we probably should have a check here that says, well, let's raise a value error and say invalid value in board file. Okay. And then at the end of this process, we're just going to return current row. And that's our function. Now, a few things. First off, good point. We could also use a CSV reader. I wanted to do this just a little bit more general and just use a file reader. Either way, there's not a special choice of one versus the other. There's certainly faster ways of doing this, both with comprehensions and other packages. I just think it's also an opportunity to show a little bit of modularity. Great point, though. The other thing I was going to ask, though, is here's my question for you. If we look at reading through the file, one of the things that we've checked is that, well, if when you read it and something is not the string 0 or the string 1, then we'll automatically produce a value error. That is good. But what is the other issue that we might encounter as we read in a board? Which is not that the values themselves are wrong. We've handled that. They all have to be 0s and 1s. But what's the other thing that we might want to check about our file? Good. So see some folks with some good thoughts here. If I make this thing non-rectangular, currently this is still going to read it in. Presumably, that could produce some real weirdnesses downstream of this. And so one of the things that we might want to do, I can't see any real reason why we wouldn't want to read in a rectangular board and a rectangular board alone. So let's ensure that it's a rectangular board. And here is where I'm actually going to go to functions.py because this is going to be an even more important function than just is what contained, you will call it in additional contexts than just parsing. But in this particular case, I've got an assert rectangular function. It doesn't return anything. But what it needs to do is range over the board, and if the board is not rectangular, meaning, well, yeah, if it's not a rectangular board, then I want to raise a value error. So it doesn't return anything, and if everything's okay, we call the function and nothing happens. No action is taken. But if we do happen to have a board that's non-rectangular, it's going to raise a value error. I think we have another way of me asking you a question, which is we need to range over a board, and the board is now a game board. Let's assume that we've parsed it, so it's not strings anymore, it's just Boolean values. But once I've got my two-dimensional list of bools, how is it that I can range over the rows and ensure that they all have the same length? How can I write this function? That's my question for you. yeah, it might sound, I think it's the type of test that could trip somebody up, right? To think, well, how do I ensure that they're all the same length? But then we realize the board is rectangular if all the rows have the same length, but all rows have the same length if all rows have the same length as the initial row. So all I have to do is figure out how many elements are there in the initial row. Because I've ensured that I know that the length of the board is positive, I know I have to have some rows in it. And so I can simply say the length of the first row is equal to the length of board of 0. And then I just range over the remaining row indices. And here's where we can use Python ranging that starts at 1, but we're going to go up to the length of the board. And after we do that, I'm going to be able to say if length of board of row. So what is the length of the current board, current row of board? And if that's not equal to the first row's length, well, then I want to raise my value error. And I'll say non-rectangular board. I could be more descriptive, of course, but that's where we know that our board is non-rectangular. And if I survive all that, I can just say no action needed, because the board is rectangular if we make it down here. Then a couple other minor points. One would be, well, okay, a couple other minor points. One would be, I've used length of board here, but really what I'm thinking about is this is the number of rows in the board. And I've kind of given you a sneak peek that I'm going to write functions to count the number of rows in the board and count the number of columns in the board. And I can update this particular function here, or this call here, to length of board with just count rows of board. Okay, so that will give me the number of rows that I care about. That's what we're going to range over. I should write those functions, and I would point out that there's natural places to put them. So we've already drawn the game of life in a previous code along, and the width of the board is proportional to, when we draw it, it's proportional to the width of each cell in pixels times the number of columns. So here's where I think we called it count calls of board is going to be used. And here the height is a function of the product of the cell width and the number of rows in the board. So I can replace that here. And this is built in, but also it allows us to say the number of rows in the board is always the length of the board. The number of columns in the board is sort of making this assumption that I know that the board is rectangular. And so you'll see I imported those functions. I also probably should, in custom IO, while we're on the subject of importing things, I should probably import from functions import assert rectangular, because we just used that and we wrote it in functions.py. So I asserted that. What I want to do is, at this point in time, I want to say, well, I've read the board from file, so the board is read, but we need to ensure that it's rectangular. And so I'll call assert rectangular of the board, and if I survive that, then I know the board is rectangular and consists only of zeros and ones, which means it was converted to trues and falses. So far, so good. All right. So we probably should save this and also run our, or write our count rows and count calls function. So this function is easy. It's a fancy way of just saying length of board. But count calls is going to be a little bit different. We need to be careful. Why is it that when we write the number of columns, we determine the number of columns in a board, we need to be careful? What do I need to be careful of? It'd be very easy to say, I don't need count calls, right? Just return the length of board 0. That's the number of columns, right? The number of elements in that initial row. What's our potential issue? Maybe I'm asking too simplistic of a question. Okay. All right. Lori, thank you for saving us. Great. It's the same issue as before. So it'd be very tempting to write a count calls function like this. If the board is empty, good question. Guess what? I check that. So if it's not a list, or if it doesn't have any rows in it, this is very dangerous. But that's why I make these sorts of checks, so that I can ensure that board of 0 does indeed exist. So it's not quite that. It's our same issue as before. The number of columns in a board may not really, and in this particular example, it's not going to make any sense to me if I'm not working with a board that's not rectangular. So I need to assert that it's rectangular if I'm being strict here first. And this shows why, when we move beyond the basics of programming, as we move into more advanced projects, these sorts of functions are actually really important, because this is fraught with peril, right? You need to make sure that what you're saying here actually makes sense. And if you're working with something with a variable number of elements in each row, the length of the initial row is the number of columns, doesn't necessarily make a lot of sense, because then it would be variable. But if it is rectangular, then you get this. And producing an error, if you have a non-rectangular board, is probably a little strong here. So one of the things that you might do is you could prompt the user to say, are you sure that this is something that you want to do, instead of just killing the program. But I think the point still stands that you want to be careful with these sort of blanket statements that don't protect yourself against other cases. Now, we've done quite a bit. We've read in our file into a board, and we've written a couple functions here just to make sure that we're doing some of the basics, that we know how to assert that a board is rectangular, and so forth. But let's go to main, and in main, let's test our I/O. So let's write a little bit of code, and we have Pygame imported, which is good. So we've learned a little previously about how to draw things in Python with Pygame. And we know that the first thing we always want to do is initialize our Pygame session. And the last thing we always want to do, pytame, is to quit it. And then in the middle of this process, let's read in our board. So I'm not typing it out. It means I can read in some larger boards than what I was working with before, where I had to type in the pentomino. I can now say our automaton that I care about is read board from file, and this just takes a file name. So the name I might give it is, let's give it boards/dinnertable.csv. And we know how to draw a game board. You'll see we have a lot of function imports here already for you. So that all is going to come from the drawing package, or the drawing file. So when I draw a single board, I'm going to say the surface that I care about is draw a game board of the automaton. And I also need to give it a cell width. We can see that because if we go to drawing, we have to give it a cell width. We also need to give it the live color. We need to give it the dead color. And we need to give it a scaling factor. So I will say that the white is going to be the live color, and that corresponds to turning the red, green, and blue channels all to the maximum, so 255, 255, 255. And let's say dark gray is equal to 60, 60, 60. I believe that's the color we used previously. So this allows me to change the colors that go in. And if we look at the drawing code, we see that the live color comes first and then the dead color. We also had this scaling factor because we're going to draw our automaton as a bunch of circles. And the scaling factor tells us how much to multiply the radius by, so that in case it's less than 1, the circles in corresponding cells or adjacent cells are not going to be tangential. So that will just cause an ugly appearance. And so we have this scaling factor. I have added something, which is that after I've declared the scaling factor, I've added equals 0.8. And this is something that we see a lot in Python. That's a good feature, which is that a lot of times I might not care about the value of this parameter. In this particular case, I don't really. And I actually could say I don't care so much about the colors either. So maybe it would be the case that I want to just have default colors if I don't tell it any colors that it's able to use. I don't mind declaring the colors, but I don't necessarily care about the scaling factor. I want the code to just work. So there's a way in Python of establishing a default parameter, which is a neat feature of Python, honestly. It allows us to say, if the user doesn't give us this parameter, the default should just be equal to 0.8. And I'm not going to give the parameter in this particular case. So that's really good. And the only caveat is anything with these default parameters needs to occur at the end of your parameter list so that everything else gets specified by the user. So you have to enter the board, the live color, the dead color, and the cell width, but you're not actually required to add the scaling factor. If you do, great. If you don't, it will just give it an automatic value of 0.8, which is pretty good. In the meantime, I'll come back to main, though, and say, in main, the whole point of me going over here was to say, we want the live color first and then the dead color. So I need to give it the live color. In this particular case, the live color is white, and the dead color is my dark gray that I just declared. And I have the cell width parameter. Now you might be wondering, where's my cell width parameter? So I need to say that the cell width is equal to, I don't know, 20 pixels, something like that. And now everything looks good. The only thing I haven't done is use the surface. So let's give ourselves an output file name. So this is reading in from the boards folder, dinner table, and I want to write to an output folder, which we can see is currently empty. So the string is going to be output / to indicate that it needs to go into this output folder. And then I'll give it in this particular case, like the dinner table file name. And I believe I need to give it like add.png. I'm trying to remember. Come back here. I think it's .png. Yeah. All right. So we're going to save a PNG. And now when we write it, we're going to say we need to call pygame.image.save, and then we're going to save a surface that we declared to this file name as output. And if we make it here, maybe we say, print board drawn to file. And if we make it here, maybe we say print board read from file. And now that I've got my code, I can save it. I can bring up a terminal. My terminal is currently pointing to the src directory within my Python folder. I can navigate into Game of Life. And I can run with Python 3 or Python on a Windows machine, main.py. I'm sure I probably have an error. I don't know. I wrote a lot of code. But we saved it all. So we run it. Oh, read from file and drawn to file. It's pretty good. Let's see. And you may have some errors too. If you do, it's probably no big deal. It's probably relating to things like making sure all of your functions are imported or things like that. So if you get an error along the lines of, I'm not sure what this function is, it's probably stuff like that. In the meantime, you'll notice my output folder now has dinnertable.png, so I can take a look at it, and hopefully it looks like what we saw before. In this particular case, it is not the highest resolution image because our cell width is only equal to 20. So when you zoom out from this, it might look okay, but make sure in the drawing, I think I made sure, yeah, we added these integers. So let me go back to main and make this 100 because it's not a big board. And then when I run this before, it gets drawn to the file quickly. And now you see much sharper resolution here because you're ensuring that the cell width is 100. And we can change this for all of our boards. So I can come back to main.py. I could run the Gosper gun. I could change that to gospergun.png and save that and run it. And now it's drawn to file, or I could do the same thing for our pentomino and then change it down here too. Probably a better thing to do would be to just have one string, but it's not like I'm going to do very much at all with this example apart from showing you these 3 instances. So that's run as well. Here's our pentomino. You kind of have to zoom in to see it. There's a lot of black because there's a lot of dead cells. There's only 5 that are alive, and they're not getting drawn. So remember that as you range through the board, you don't actually take the time to draw it if it's dead. So that's why this was so quick to run. Here's our Gosper gun initial state. So it doesn't look like much now. And the reason why is because we need to animate this stuff, but we can't animate it unless we can actually produce the engine. That's what I want to do. But the first thing that I want to do is prepare myself to perform that animation. So in the drawing file, there's one more function that I want to write, which is I've got a list of game boards, which I'm going to call boards. These are the generations of the automaton. And I've got a cell width, which is an integer. And then I want to produce this list. And what is the list? It's a collection of surface objects. So it's going to draw one surface for each board in this list of boards. Again, thank goodness we have the game board alias because I can think of the inputs just as a list of these objects. And you might think this is a challenging function to write, but it's going to be indicative of something that we've already seen and that we'll see later tonight again, which is that if I can do something one time, it's really easy to do it n times. So in this particular case, the list that I care about, which is going to be a list of game boards, is just an empty list. And then I'm going to range over the boards that I have. Board is a game board. Why? Because when we range over a list, you get the things that are in the list. So for each game board, I'm going to simply append the result of drawing the game board with the current board, with the cell width, and I could leave this blank, and that would be fine. It does seem weird that I wouldn't give it a scaling factor here too. So I'm going to give it a scaling factor, and that's a float equal to 0.8. So I'll pass the scaling factor down in that way. Okay. And then at the end of this process, I'm simply going to return the result. So what is this result? I could even call it canvases, right? It's a bunch of pygame.surface objects. So all of my that's one canvas, so to speak, one virtual object to represent me drawing on something, one for each generation of the simulation that I have. And as I said, it's a short function. It's just a few lines where at each point in time, all it does is range over the list and it draws each one. And when it draws each one, it appends it to our growing list. And that's it. That is it for drawing. Let us know if you have any questions. In the meantime, I think there's like some kind of either motorcycle rally or heavy industrial operation going on outside my window, so I'm going to sit perplexed over what that is. But we know how to draw boards, and now it's just a matter of doing one other thing, which is to make the simulation that we care about. And that simulation that we care about is going to implement the game of life. It's going to be in my functions.py file. The setup that we're going to have is ongoing with this folder that we're producing. So we've written some code in custom IO. We know our data types. We've done the drawing. We've even started writing code in main.py. And we've even written 3 of these relatively simple functions in functions.py to count the number of rows in a board, count the number of columns in a board, assert that a board is rectangular. We've got all that covered. What it remains to do is to write all of the functions to actually simulate the process of implementing the game of life. And by that I mean, here I can point you to in our images. I have this is a little bit grainy, apologies for that. But we have what I like to call a function hierarchy that indicates which functions call other functions as subroutines, and to lay this out as a network of sorts. So at the level of pseudocode, if you did the reading accompanying the code along, then you'll have seen this because we walk through how we would think through, without even programming a single line of code, how is it that we would think about organizing our project. And the project is organized in this way, where we have a function to play the game of life over a number of generations given an initial board. That winds up calling a subroutine that updates a single board's generation. That has a bunch of subroutines in it, like updating a single cell. We've written count rows and calls. We also need a function to initialize a board and create a bunch of default values. We've got this count live neighbors function that counts the number of neighbors in the 8-cell more neighborhood of a cell that are alive. And then we've got this in-field function that determines if a given cell is actually on the board. All important stuff. What I would ask you is, where in this function hierarchy should we start? If I'm going to go to functions.py and write all of these functions, where is it that we should begin? All right, some varying opinions. Some say the top, some say the bottom. No one says the middle. I guess we already did start in the middle because we wrote count rows and count calls already. Okay. I'm going to argue, and the spirit, sort of the high-level concept that we're trying to get at with this entire chapter, is top-down programming, meaning we plan the code to start with what it is that we truly care about, which is solving the game of life. And how I could frame that as a computational problem is to say, I start with a board, and I know the number of generations that I want this thing to run for, and then I wind up with a collection of numgens plus 1 boards, where you have one corresponding to each generation of the game of life. That's how I think about the problem. That's what it's like keeping the end goal in mind, right? It's like, that's what we want to do. And then on the way there, all these subroutines are just our minions. They're just there to help us. And what you will find out is, even if you have a good plan, A lot of times if you start at the bottom, you'll work your way up, and then you'll realize when you get towards the top, oh man, I didn't even need that subroutine, or that subroutine needed this additional input, or I need another subroutine that's going to live here, and it's going to change your entire hierarchy. And one of the benefits of planning everything on the level of pseudocode and thinking through exactly like on a whiteboard, literally, how it is that you want everything to work, one of the benefits of that is to get all these ducks in a row before you start coding. But then there's another strong way of going about it, which is to start with the function that you ultimately care about at the top and work your way down so that you know at each point in time, you're pretty sure that this function is more or less exactly what you want. And if I think about what is it that Play Game of Life needs, it just needs the initial board and the number of generations. And so that's the function I'm going to start with. So I want to write a function that's just all it's going to do is, well, exactly what we want the simulation to do, which is to play the game of life. So it takes this initial board as a game board. You'll see I imported it above. And it also needs to take the number of generations. As a result, it's going to produce what I said before we thought of in two ways. The first way we thought about it was as a list of game boards. And the second way we thought about it was as a three-dimensional list of bools. This is just a nicer abstraction, so that's what we're going to go with. I added a little bit of code for us. So I want to make sure that there aren't 0 elements in the first row. That would be bad. I've already checked that the number of rows is positive. And I also want to make sure that I'm working with a rectangular board. I can probably overdo it with all these assert rectangular checks, but you could also point out that, well, it's only one line of code, and it's like a good line of code that's making sure that everything's okay. So there's nothing wrong with adding it a little bit too much. And now it's just a process of writing the function. So I'm starting at the top, and you might be worried to say, oh, this is going to be a complicated function. But actually, it's the exact same thing that we saw when I was drawing multiple boards, which is that if I want to simulate the game of life over multiple generations, well, I'm going to start with a list of game boards that doesn't have anything in it. And then technically I want it to contain the initial board that we're working with. So I could have done this in one line of code, but there's nothing wrong with this. And eventually that's what I want to return. And in the meantime, well, I'll say range over the number of generations and update the previous generation to give the current generation. Sounds easy. I'll range over the numgens that I care about. And I'm going to say, well, the previous board that I'm interested in, so this previous generation, it would be very tempting to type I-1. And if you had done your ranging in a little bit of a different fashion, then that would be okay. I'm letting I range between 0 and numgens -1. So for that reason, the previous board needs to start at boards of 0. Not I0, boards of 0. Boards of I. Okay. So when I is 0, that's where it's going to start off. So previous boards is always boards of I. And then I'm going to append to it the result of calling a special function that will update the previous board. Again, I could do this in one line. I'm going to do it in two. So this is the previous board. I'm going to call update board to give me a brand new board corresponding to the next generation. And then I'm just going to append this thing to the list of boards that I created. Again, you might want to do it like this, 1 to numgens +1, and then you would need to make this a -1. It doesn't really matter. Either of those ways is pretty equivalent. All I'm trying to get you to see is a couple of things, which is number one, look at how easy this is. Okay, yes, it's a lengthy doc string, and I make sure I do all my error checking because it's worth preventing an error in the long term, just with some of this standard checking. But the function itself creates a list of game boards, appends the initial board to it, ranges over all the generations, and simply says update the previous board, and that's your new board. And then at the end of this process, I'm going to return my list of boards. So look at how easy and natural writing code in this way is. And yes, you then need to write the subroutine, But I have taken what started as a complicated task of simulating the entire game of life over potentially 10,000 generations. And regardless of how many generations I care about, I've now reduced it down to updating one single generation. And I'm going to do the same thing as we move down the hierarchy, and you're going to see how natural each function is. Whereas if we start with the hardest possible task, something that I've seen folks who don't have a lot of exposure to programming try to do for a lot of years, and this I found was like the perfect module, the perfect way of teaching this, because it's not a huge programming project, and yet it really gets at the point of you will sit down and worry about all the different ways. Where are the rules going to go? How do I handle like cells that are off the edge of the board? Like everybody thinks about these as very natural things to do, right? So like, well, what if I look up here at this corner and I want to consider its neighbors? And, you know, I guess they're all considered dead, but how would I access all of these elements and make sure that everything is working? These are all perfectly reasonable human things to worry about. But remember, we're in the realm of computer science. That means we're lazy, but it's also immensely profitable, both literally and figuratively, to think in this way. And so that's how we're going to do it. And what you're going to see is we unravel just a little bit of difficulty every time we work our way down the function hierarchy. And then these details that you might have thought were super complicated wind up being like, you know, the monster under the bed. They're not scary after all. So that's one other point I wanted to make. That's observation number one. The second observation I would make is what isn't present. And maybe we'll see if you get at what I'm going for here. But what is not present in this function and our implementation of it that you might think might be present as part of an implementation of the game of life? What isn't here? A couple answers. The rules are not present. Fair enough. You're right. They are not present. And that's what I'm saying in terms of delaying our gratification. So we're going to hold off. The rules and the number of neighbors and these complicated details are not present. I would roll that into my statement about modularity and top-down programming and saying that we're delaying caring about all that, because I don't need to care about that in order to write this function. It's kind of convenient. We'll let the minions handle it. We do have another point. I don't know where my voice went. We do have another point that's good, which is that this has nothing to do with the drawing. And in fact, you're not going to see anything to do with drawing in this entire file that we write with multiple functions. It's another thing that a lot of folks who come to programming for the first time, I've seen a little bit of confusion around that. Well, I want to visualize this too. And to separate the notion of generating data from visualizing data. We've already seen that, I guess, a little bit when we looked at prime finding algorithms and we wrote an engine to make the collection of all the primes up to a certain point in time, and then we visualized the primes. And the same thing is at play here. You might want to make something that's producing a visualization in real time, and if that's a critical part of your program, great. You're going to intermingle these. But for this sort of task where I want to make the visualization, and I probably can just store all of the data for that visualization separately, well, why don't I run the engine of my code first? And then I can make the visualization code just serve the needs of the visualization. It's the type of thing that I'll see beginners intermingle when they don't need to. And it's the other point about modularity. I'm modularizing both the engine of my code and the drawing. I'm keeping those two tasks completely separate. So the drawing's already been done. I don't have to think about it. And in the meantime, what I care about is going back to functions and carrying on down my function hierarchy. So as I go through this, I'm going to say, update board is the next thing that I want to write. What does it take as input? A game board. What does it return? A game board. That's nice because it takes in the previous generation and it gives you the next generation. So we need to implement this. And to implement this function, we'll say, first, we probably should, maybe we could assert rectangular, or maybe we could copy down some of this other stuff that I've got in other places. But assuming that we've done that, the next thing we want to do is first make a new board. Okay. And in order to make the new board, actually, I'm not going to worry about asserting rectangular because I'm going to call the count calls function here. So I'll say num rows of the board that I need to make is, well, let's call count rows, or I could just do length of the input board, which is my current board. And num calls is equal to count calls of my current board. And now what I want to do is make, so when I make the board, having a bunch of default values with dimensions equal to the previous board. So here is where I will say my new board is equal to a function that I'm going to call initialize board. That's simply going to take the number of rows and the number of columns, and it makes a rectangular board of that size. So I know that the dimensions of the new board are the same as the current board. It's going to get a bunch of false values that are just the initial default values that I want to work with. And then after I've made this thing, and I'm going to pass that work to a subroutine. So you might say it's not a long thing to do, and I'll say, yeah, absolutely. But this is the sort of code that would be very potentially reusable, right, in other contexts, which is just to make a board. And yeah, we could also just use a Python one-liner, but these sorts of things don't exist in other languages, and to me, this is not going to take any longer. It's also less ugly. So once we've made the board, then I can assume that it's there, and we're going to range over all the cells of the current board and update the corresponding element of the new board. So I will say, let's for r in range over the num rows. So we have a row index, and we're going to get a column index. And here's, an acceptable form of a nested for loop ranging. And then we're going to say, all right, as we do this, the new board of RC is simply equal to, and here I could worry about the rules and this sort of thing, but again, I'm going to keep passing the buck down the line and say, let's delegate this to yet another subroutine. And that other subroutine is going to say, I'm going to call update cell of the current board R and C. And so I'm simply passing into that function exactly what it needs, which is I need to know the board, and I'm going to update that current board's cell at R and C. So I'll look at the previous board's position and its neighbors at this specific row and column index, and then update cell is going to give me a true or a false. So it just depends on what the output of this function is when it consults that element. That's where the rule checking is going to take place, is deep within this update cell subroutine. So I'm delaying this for as long as I possibly can, because if I assume that somebody has given me that update cell function, I'm now done because I know it's got the right dimensions and I've ranged over it and I've set all of its values. And so at this point in time, I'm simply going to return that board. I've got two subroutines that this function called. Well, I've written count, I've got 4 because I've written count rows and count calls, but there are 2 that I have not written. One is initialize board. The other is update cell. Which one of those is harder? Update cell, so I'm going to write it second. let's be lazy. In the meantime, I'm going to write initialize board. I'm going to start by creating a blank board. So it's just an empty list. That's what I'm eventually going to return. And in the meantime, I'll say range over all of the rows and make each individual row. So for underscore, because I don't care about the integer index, and ranging over the number of rows. And in this particular case, then I say row is equal to a bunch of false values. How many false values are there? It's numCalls. And then I'll say board.append this row. Okay. Remember, you don't want to do this with a single line. So we saw I was trying to prepare you for this specific moment when we looked at two-dimensional lists. And you'll remember one of the things that we got tripped up by was trying to do a line like this, and then instead saying my board is this false times numCalls, and then saying it's this times numRows. And that looked like the most natural thing in the world, except that it winds up meaning that when you change one element of one row, it updates all of the rows. So we don't do that, and instead, it's not a big deal to write a little bit longer of a function to initialize our board. So the board just starts off as having a bunch of false values. So we've declared our game board here. We create the row, we append the row to the board, and then we return the board. And now we can move to update cell. So now we can look at our other subroutine. And our other subroutine takes the board, it takes the row and column index that I care about, and it returns. Should the updated value in the next generation at this particular cell of the board be alive or dead? So should it be true or false? We have some checks for us down here. What I really want to do is figure out what are the neighbors of the current cell and how do I apply the rules of the game. So I'm finally able to really apply the rules of the game. And so now that we're at this point, we're kind of heading towards finishing our simulation, because this is where we as humans think about how the game works, which is, and I've got our rules, so let's refresh the memory of the rules, but there are 5 rules, simplified, in the game of life. So the game of life says we've got a two-dimensional grid of cells. They're all either alive or dead. And then in the next generation, there's 3 rules corresponding to this fact that a cell is currently alive. And these rules roughly represent life in the sense that if the cell is alive and it doesn't have very many neighbors, I'm going to call that the lack of mates condition. So that's rule B, and it's going to die out. Similarly, if you have too many neighbors, it's also going to die out. So we call that an overpopulation condition. And if you're in this sweet spot of 2 or 3 neighbors that are alive, and you're alive, you're going to remain alive in the next generation. So all of the cells in the game, in the entire board, are like playing this in parallel. So when you go from one generation to the next, they all apply these rules, checking their neighbors in the current generation, and then updating to the next generation. If a cell is dead, I think the original formulation of the game said it's going to remain dead. There's no reason to bring it back to life. And what makes the game have its special properties, really, is that you have a zombie state, which is that if the cell is dead and it has exactly 3 live neighbors, then it has this opportunity to spontaneously regenerate into an alive cell. So these are the 5 rules of the game. They're all based on the number of elements in the more neighborhood of a cell, meaning the number of live neighbors, I should say, in the 8 cell neighbors corresponding to the 4 elements of this green cell that are directly adjacent to it, and then these 4 diagonal elements as well. So some cellular automata use what's called the more neighborhood, which is this 8 cell neighborhood Others apply rules using the 4-cell von Neumann neighborhood. And so that's when we look at more generalized cellular automata next. My favorite automaton actually only looks at this 4-cell neighborhood, but it just depends on the automaton that you have defined. So sometimes you look at 4 cells, sometimes you look at all 8. The game of life applies all 8. So when we say it has 2 or 3 live neighbors, it means in this 8-cell neighborhood. So the idea is, how do we take these rules and then apply them to our function? Hey, that's a great question for you. So think about it for a minute, and you tell me, how is it that I take the 5 rules that we see here and then apply them back to my function of update cell? How do I convert this? Some great ideas. I like that there's the thought about using a match statement, or what we might call a switch statement. That's really good. And I like the idea that we could branch. We need to branch in one of 2 directions. So one of the things that we might do is to first check how many neighbors there are of a cell. Because, for example, if it's not 2 or 3, then you're done. You know that it's going to be dead in the next generation. You can return false. And then if it's 3, you're always returning true. And if it's 2, well, it depends. If it's alive, it's going to stay alive. And if it's dead, it's going to stay dead. So that's actually really cool. I like that idea a lot. And I don't think that I've seen it before, although now it seems like it makes a lot of sense. It will definitely be faster than what I do, which is I'm first going to check, is the cell alive? Because I like just conceptualizing this particular game as saying, is the cell alive or dead? And then branching into the 5 specific rules, which I guess we can summarize with less information. But I care about 2 things, regardless of how I'm implementing it. Number 1, I care about how many neighbors of the cell there are. So we should write a subroutine and pass all that work to our minion to say number of neighbors is equal to count, and I'm implying here that the number of live neighbors is count the number of live neighbors of board R and C. So how many live neighbors are there in my 8-cell more neighborhood that we talked about? Once I've got that number, it's pretty useful. So I can simply say, we're going to have, let's branch into 2 cases, current cell, alive or dead. So I'll say, is it the case that board of RC is true? This is the live case. And then we're going to have an else, which is the dead case. And we can look at each of these in turn. So I'm going to say, if it's alive and the number of live neighbors that I accessed is equal to 2 or it's equal to 3, then in that particular case, I want to return true. And in all other cases, I want to return false. So there's a little bit of nesting. It's not the end of the world. But I think it's probably fine. You have your alive case, and then we have a quick if statement. Say, is the number of live neighbors 2 or 3? If so, return true, because you're going to be true in the next generation. You're going to remain alive. So this is remain alive. And this is either lack of mates or overpopulation. So you either had too few or too many live neighbors. And then when you look at the dead case, then there's only one possibility, which is that the number of neighbors is equal to 3. And in that case, I'm going to return true. And this is our zombie case. And then otherwise, I'm going to return false. And this is our rest in peace case. The normal, most cells that are dead don't just spontaneously regenerate as alive. So now we get down to the nitty-gritty. We've worked our way down in the function hierarchy. This was a little trickier than what we did. But at the same time, I'm still not worried about things like the edge cases. I've still somehow pushed this all the way down the function hierarchy into this subroutine that just counts the number of live neighbors of the current cell of the current board. And that task is seemingly not very advanced. It's so separate from all these higher level things that we've done of running the game of life, initializing the board, updating the cell. All of that has already worked without having to worry about any of those possible conditions. And so now we get to write our count live neighbors function. And this is where, again, to refresh your memory, we have a current cell at row R, column C, and we're interested in determining how many neighbors in this 8-cell neighborhood are alive of this cell. So how many true values? And John compliments me on the structured procrastination. And if you think it's over, it's not. So I'm going to keep procrastinating. And I'm going to show you how I'm going to keep procrastinating here. The way I'm going to keep procrastinating is just to say, what are the annoying cases? And the annoying cases are what we mentioned briefly, which is like if you have the dinner table and you're looking at this cell here, it'd be like having to consider something on the boundary, right? Because then you've got to consider what happens, if I try to access this cell, for example, it doesn't exist. So the last thing I want to get is like an out of bounds error because I tried to access something that's in a column that's too big for the element. Or I'm down here, for example, in this bottom row, and I try to look at this cell and I try to access it, and then Python gives me an error because I access something that's off the board. The answer to all of this is just to not care. And I know that sounds weird because you're like, well, you're just wandering into an error. And we know that this boundary is the hardest part of it. So I'm just going to ignore it. And so that doesn't mean I won't eventually clean it up. But I'm just going to say, how many neighbors are there? Well, we start at 0. Is that what we're going to eventually return? Yep, we're going to return it. And then the only thing I'm going to care about is, how do I access the neighbors, the 8-cell neighborhood of my current cell? I probably need a for loop. And the question is how? What do I actually do in order to access those? So you tell me, what code needs to go here if I'm completely ignoring boundary cells and just saying, I don't mind, I'm willing to encounter an error? What does this become? So Roy has one idea. One idea is we could make a 2D tuple, I guess, since we know how big it needs to be, corresponding to the neighborhood. And that's a perfectly reasonable idea. I don't like it because, for one specific reason, I'm now making more data. But do I need to make more data? I don't think so. And it's not like it's going to cause the the runtime or the memory to blow up or anything like that. It just means that when I start making something that I don't need, all that does in my mind is incorporates the likelihood that I will mess up in making that data. And now I've got one copy of the data that's right, and then another copy of the data that's just wrong. And I've got to somehow figure this out, because then I might encounter a bug. And I was thinking, oh, I thought maybe that I had read in the matrix wrong or something. But no, actually it's that I made the new matrix wrong. And so it's a perfectly reasonable thing to think. But the question is, how do I do it without making something new, right? Because I don't need to make that thing new. I just need to range over these values and count how many cells are alive. Okay. So a couple of good ideas here. Claudia's got a good idea, which is, let's look at the picture. And if I look at the picture, then I know I need the rows between r-1 and r+1. And I need the columns between c-1 and c+1. And you're going to worry about something, which is, well, I don't want to consider myself fair. Guess what I'm going to do? Not care. So all I want to start with is remembering that I'm intentionally walking into a mistake here. I just want to range over all of the values where the rows go from r-1 to r+1 and the columns go from c-1 to c+1. And now I realize, okay, well, how do I do that? I'd say better idea, range over just the values that I care about. So I will have a for loop then that says for I, and I is going to represent my new range, my new row values. And the reason why is I already have R and C spoken for, so I don't want to use R and C. They're fixed. But I'm going to range I between r-1 and r+2. And I'm going to range J as my column value between c-1 and c+2. Remember, we're not going to include r+2, so this is going to take me r-1 to r+1. This is going to take me c-1 to c+1. And then, well, I'll say, is it alive? And if so, well, I want to add it to the count. So I'm considering the current neighbor, and here's where being nice and steady is very helpful, because it's so tempting to type something like, is it the case that board of RC is true? But it's not board of RC that you care about. It's all the neighbors of board of RC, and the current neighbor I'm interested in is board of IJ. So when I change this to board of IJ and say, is that true? Well, it's alive. The neighbor is alive. Count plus equal to 1. And now I didn't have to make new data. I didn't have to make a new two-dimensional list and incorporate the potential of an error there. I just said range over the neighbors and in this way. And if the current cell is alive, then add 1 to the tally. And then at the end of this process, you return the count. Now, you probably are worried because I even told you this function is blatantly wrong. And then the question is, how do I fix it? It's almost, if you know you're intentionally making a mistake and it's right there and you write down what it is that you need to address, it's almost refreshing or like freeing, liberating, I should say, to write a function in this way, because you're like, I know that there are going to be hard details, but there's only so many hard details I as a person can hold into my brain at this point in time. So let's keep only the detail of doing this ranging, and then we'll worry about everything else. Now that the ranging is done, my question for you is, all right, let's fix it. But keeping in mind the two things that I care about, number one, this currently includes the current cell, which I don't want to do. I only want to consider its neighbors. So I want to kind of cut the hole in the donut, so to speak, and not consider all 9 of these cells, but consider just the 8 that are not equal to myself. That's issue 1. And issue 2 is, what if board of RC, as we have said, happens to be like on the boundary here? So if that's the case, when I range the R up to R+1, this is where I'm going to get my index error. And so I know this is going to give me a problem. So I have to address both of these issues. One, I'm including the central cell as part of the neighborhood, which I don't want to do. And two, I need to handle the border. And the question is, how is it that I would do this, keeping in mind we're trying to be lazy, with as minimal effort as we possibly can use? And my hint is, we should probably think of these one at a time. We shouldn't try to do both concurrently. So what can we do? So critical point, I don't know that the current cell is alive. At no point have I asserted that board of RC is true. It could be alive, it could be dead, and it's useful in both of these cases that we've considered before. So some folks are saying, oh, board of RC is alive. Well, not necessarily. Another point we need is to check if the cell is in the board. So is it the case that board of IJ is in the board? Board of RC is certainly going to be on the board because, well, when we've done this, we've called it in a very precise way to ensure when we call update cell, we're ranging over all the rows of the board, and C is the columns of the board, and we're only going to call update cell of RC, which means when we call update cell, we're only actually going to call count live neighbors of RC. So R and C are always going to be on the board, but a neighbor might be off the board. And in particular, what that means is board of IJ might be off the board. So that's a good point too. So it's three things that we need to have happen. We need board of IJ to be true, but we also need it to be on the board, and we also need it to not be board of RC. So all three of those things have to be satisfied. I like one idea that I saw. One idea, because I think it's really clever, is to do something like if board of RC is true, count minus equal to 1. That's really a nice idea. We overcounted RC if it's true. If it's not, we didn't. So it's alive. So we counted it as one of the live neighbors, but it actually wasn't a neighbor, so I need to subtract it. This is hard to criticize. The only way I would criticize it is to say it somehow doesn't reflect how you would explain it to someone, right? Like if you were telling, you could train a child probably to learn how to do Game of Life and color in the cells. We should do that. Game of Life is really neat. But you probably wouldn't tell them to do this, right? You would tell them to just, well, look at the cells around you. And you've got how many cells around you at every point in time. I don't know where my images went. You got the more neighborhood. You have all these 8 cells. Every point in time, count up how many are alive. Well, they would automatically not count that cell if you told them right. So you said, don't count that one, right? Instead of, oh, count up all 9, and if that's true, subtract 1. So one of the things that we want to do, and this isn't always the case in programming, but one of the things that we want to do is anytime we can, we should probably have it so that the implementation reflects how we think about it, because then when we look at the code, it makes sense. And so I won't quite do it that way. What I will say is I can just type something that's nonsense here, which is the current cell is not equal to RC. That's important. So I'm not at this current cell. And then there's a third thing that we want to check, which is that IJ is indeed on the board. Now, again, like I said, I intentionally wrote code that was wrong. Here I'm intentionally writing code that's not even Python. And then you think, well, I needed to handle how to do both these things. A couple of you in the chat, well done, already told me how I check if RC is not equal to IJ. I could say, well, this only happens if two things happen to be the case. So R and C is not equal to IJ if one of two things is the case. If R is not equal to I, or if C is not equal to J. So when we look at our Moore neighborhood and you think all of these cells are going to be valid as long as it's not the case that R is equal to C, or I is equal to R and J is equal to C. If either of them is different, so like this cell, okay, well, I here is equal to C. Oh no, or J is equal to C, but I is equal to R minus 1, so it's different. So we can handle this by saying, okay, well, what I'm checking here is a big parentheses. And inside of that parentheses is I is not equal to R, or J is not equal to C. That's what it means. And hopefully I've convinced you that that's the right logic. But it turns out that I'm actually able to do this with something simpler, which is, remember how I wanted to think about this, which is that the second condition that I care about is that IJ is not equal to RC. So the current cell I'm considering is not the central square. This is a tuple. This is a tuple too. Python includes built-in support for checking if two tuples are equal. And they're equal precisely when I is equal to R and J is equal to C. If those things aren't the case, then the tuples are not going to be equal. So for example, the tuple 0, 0 is not equal to the tuple 0, 1 or 1, 0. So it turns out that this, which is very humanish, right? It makes a lot of sense to us, is actually built in to Python. And I get to, like, the confetti gets to rain down on my head because I get to say something very nice about Python. This makes all the sense in the world to be able to check ordered pairs like this and say, I can see if two ordered pairs are not equal to each other. So Python gets a million points tonight. I'm in that good of a mood. This is automatically done now. And so all I have to do is say, well, I've got to handle this. I've got to ensure that IJ is on the board. And it's either on the board or it's not, which means it's either true or it's false. And now I should be thinking of the special S word called subroutine. Claudia got it. A couple other people got it. Thank you, which is to say we're going to write in field of board IJ. It is so tempting here to put R and C. I know, right? And these are the sorts of bugs that are just a train wreck to try and fix, even if you have good testing. So in field of the current cell that I care about, which is not RC, that's the central square. It's the current cell, which is board of IJ. So if all three of those conditions are true, the current cell is true, so it's alive. It's not the central square of the neighborhood, and it's on the board. You know, if all those things are true, we're going to increase count by 1. And now, going back to our image from before of the function hierarchy, we've got it down. Like, this whole thing is starting to unwind. It's hard to believe because we've written quite a bit of code, and it doesn't maybe seem like there's light at the end of the tunnel. But at the end of all this, all we have to write is a function called inField that returns true if IJ is a valid cell on the board, and false if IJ is not a valid cell on the board. My question is, how do we do this? How do I check if the cell IJ is actually contained on this game board that's a two-dimensional list of bools. If you need a picture, the picture is to look at a sample board. And I don't have my grid lines, but to look at something like my dinner table, you can imagine the grid lines are there. And to say, what are the conditions where we would say it's on the board? And what would it mean if it's off the board? And there's two ways of writing a function like this. One way is to check that it's on the board. The irony is that it's actually a little bit easier, right, to check if it's off the board. Like, for example, if the row index is too big, so I is bigger than the number of rows, that would be bad. Similarly, if I went this way, well, that would mean that I is less than 0. Same thing for j being too far left, it would be less than 0, or j could be over the number of columns. So if any of those things happens, well, we're in one of those 4 like quadrants, and we know that we're not on the board. And if we survive all those checks, then we know that we're on the board. So I like writing the function a little bit better that way, which is to say, first off, let's check the bad things that could happen, which is it the case that I is less than 0 or j is less than 0? In either of those cases, I'll return false. So that's too small. Otherwise, if a is at least equal to the count rows of the board, or j is at least equal to count calls of the board, then I'm going to return false. And remember, this even has a built-in assert rectangular in it. And then I survived all the checks, so I must be on the board. And here's where we're going to return true as the default. And just like that, our entire engine for the game of life is now finished. We've written all of the functions from the top down. And you'll notice, I hope the biggest kind of learning objective I would have is the benefit of modularity, the benefit of careful planning and working your way top down. And then just delaying the fear of the complex details until the last moment. All of this code is actually pretty straightforward. The whole thing, we got 200 lines of code. Nothing that we did was a big step today. Certainly writing a lot of code was, but I mean, some of these functions are very short and they're all docstring. And we're able to play the game of life just by saying, I play the game of life, I update the board, I update the board, I update the cells. I update the cells, I need the number of live neighbors. That's important. And then only when we got to the number of live neighbors, this is the only part of the code that's even tricky. Even when you write infield, it's easy, right? We went through it in 3 minutes. And so it's just this ranging and making sure that I don't need new data to do this. I just need the appropriate ranging over the data that I have and this part of it, right? And so these are the only tricky parts. Most students I've seen come to a problem like this when they're just getting started with programming. They want to focus in laser attention on this. And you think if you did that, you would get code that looks like this? I guarantee you that you wouldn't. All right. If only we could see it. So we can simulate these boards behind the scenes and call a function that's going to play the game of life. So we know, for example, that we're going to call a function called play game of life on some initial board. And it's going to need to take, I don't know, the cell width. We don't need the cell width. We need the number of generations. Okay. And that's going to give us a collection of boards. Why? Because when we looked at functions, we can come to the top of our function hierarchy and we say we take an initial board and a number of generations. That doesn't have anything to do with drawing. So in main.py, we want to do this. We want to call our game of life function, give it the initial board and the number of generations. And after this process, Then I want to visualize the boards. So this is going to be like a play game of life. And then what we're going to need in the meantime is read in the board from file. So those are our steps that we're going to have. And by visualize the boards, I mean draw the boards to a list of surface objects. And then we're actually then going to have a final step, which is not to just draw them to this, but produce an animation of the drawings. And those are our 4 main steps. And this will be, what I'm going to do is I'm going to take this, and take all this code, and I'm going to keep the init stuff. Well, I'll just copy it over. So I'm going to cut it out of here, and I'm just going to put it in a separate function called read board example, something like that. And then I'm just going to put it all down here. Okay, so that was our initial example, just to clean it out from main. Because what I want to do is actually have a main that runs the full game of life. And so the first thing I want to do is read in the board from file. But before that, I will say how I would like to run this code is to go into the command line. I want to be like a real programmer and go into the terminal. And I want to say Python 3 main.py. And then I want to say, you know what? I want to run my code on settings that I control. And so I'll say, I want you to go into boards and I want you to access rpentomino.csv, and that's your initial file. And I want you to write this to rpentomino.gif or MP4 or whatever. And I want the cell width to be 20 and I want the number of generations to be 1200. So I want to call my code in this way. If I want to do that, that means I need to be able to take command line arguments. And we're going to have sort of a conclusion to talking about lists. We've talked a lot about lists. This is the perfect way of having a capstone on talking about lists, because when you run a program in this way, so when you run a program with command line arguments, they are created behind the scenes or entered in behind the scenes, put behind the scenes, okay, into a list of strings. So, for example, when I run it in this way, board/rpentomino.csv is one string, output/rpentomino is another, 20 is another, 1200 is another. And this special list of strings is called sys.argv. And you'll notice I've imported sys. So that's why, because I want to use this special list of strings corresponding to the command line arguments that are going to change every time I run the command or run the program. So that's why I have import sys. I will say sys.argv of 0, remember it is a list, is the name of the file, which is just main.py. So it's just a string corresponding to the name of the file that I'm running. So you see it here actually when I tell it what to run, that's going to be sys.argv of 0. The remaining elements are the parameters. And I want to dictate how the user, what did I do? I don't know what I did. I want to dictate how the user gets to run this. So the first one, which is sys.argv of 1, is the input file as CSV. Okay. The sys.argv of 2 is the output prefix. Sys.argv of 3 is going to be the cell width in pixels. And sys.argv of 4 is going to be the number of generations. Okay. So I want to process these. And what's nice is that the input file name and the output prefix are both strings. So I'll take them straight in from the user, and that's awesome. So in particular, what I mean is I'm going to say that the input CSV that I care about is equal to sys.argv of 1. And the output prefix that I care about is sys.argv of 2. And then the cell width is equal to sys.argv of 3, but remember it's a string. We want it to be an integer, so I need to make sure that I parse it accordingly and convert this to an integer. And the same thing with the number of generations. So the number of generations is equal to int of sys.argv of 4. So I've read these 4 parameters that I care about. Notice number of generations got colored blue down here because now I'm using it. I just need to read in the board from this particular place. And so I'll say, well, the initial board is equal to read board from file. And when I read the board from file, I just need the file name, which is input underscore CSV. And now you see this gets colored blue too. So I've not looked at output prefix or cell width yet. But I don't need that to play the game of life. So what I will do, for example, in the meantime, is to just say print board read from file, playing game. And then let's give another update to the user at this point in time to say we played the game of life. Okay, and now we'll say drawing boards to surface objects. But we've already done that. When we looked at drawing.py, we wrote a function called draw game boards that takes my list of boards and it takes my cell width parameter. I'm not going to specify a scaling factor because I have a default. So here's where I'm going to draw all of the individual boards. And I've realized that I've done one thing, but give me 1 second. So I have an error there. So I'm going to draw the boards. And when I draw the boards, I want to say, let's establish the surface objects, which I could call like surfaces, is equal to draw game boards. And here's where it needs to take these inputs. And this is I'm actually going to turn my error into a teachable moment, which is that I have a draw game board function that I wrote before I wrote draw game boards. And if you look at the parameters of draw game board, it's got the live color and the dead color in it. But notice I didn't give those parameters to draw game boards, and that's really kind of important. So I need to make sure, let's correct this mistake, which is after the game board and before the cell width and scaling factor, I need to make sure I have the live color and the dead color. So those both need to come in here. And then I can have the cell width and the scaling factor. And technically I probably should perform some extra checks here, but I'm not going to do that in real time. And we should update the arguments here. So I've got the boards and we have colors as tuples corresponding to the live and dead cell colors. Okay. So we're still going to do this, but now I need to make sure that when I call draw game board, it should get the live color and the dead color. So it will give it the live color and the dead color. Now that I've cleaned that up, when I call draw the game boards, I'll have all of those parameters. So I have the board, the live color, the dead color, and the cell width. You could perhaps give this as input to the user, or control to the user, so the user could specify what they want the colors to be. In this particular case, let's just declare the colors to be gray and white. So we're going to say that white is equal to 255, 255, 255, and dark gray is equal to 60, 60, and 60. And now I'm going to draw the game boards, and I'll look back and say this takes 5 parameters. It takes the boards, the live color, the dead color, and the cell width. The scaling factor is going to be a default. So I'll say it takes the boards. So this is all the generations. It takes the live color is white, the dead color is dark gray, and the cell width is the cell width. And now I've got a collection of surfaces, one canvas object, like these virtual canvas objects, for each generation of the board. And they're so close to us being able to see them. One of the things we could do, I'm sure, we could make a PNG for each element in this surfaces list. But it would be much nicer to make an animation. So at this point in time, I'm going to say boards drawn. And I'm not using surfaces, right? And so this is going to be a very disappointing. Let me clear this terminal. I don't know where I got out of line there. I think I've entered. I don't know what I've done. Okay. All right. So I'm going to cd into Python src. All right. And then I'm going to cd into game of life. And now I can run this thing. So I'm not actually going to see anything because at the end of this, all I did was draw the boards to files or draw them to surfaces, but I can't see them. But I do want to make sure, in the spirit of making sure that everything seems to be at least running, I'm going to run python3.main.py. And then here are the opportunities for me to run the parameters that I care about. So let me start with something simpler. I don't want to run the R pentomino for 1200 generations. Let's do the dinner table. So we know that the dinner table is present in the dinner table.csv within boards. So I want to come down here and say board/dinner table.csv. And then the output is going to be an output, which I'm not even going to use this yet, but it's going to eventually go into output/dinner table. And then I need to give it let's give it a cell width of 20 and a number of generations of 60. And then we're going to run it. And I'm going to get a list out of range. Okay. So here's where we get to the opportunity to debug live, which is always fun on like 400 lines of code. And what I will see is, this is what I ran. And it gave me line 187 in count live neighbors if board of ij, and it's saying if list index is out of range here. I don't know. Count live neighbors, board RC. So I made this call. This was an update cell, update board of the previous board. Initial board number generations. I need to check in field first. Yes. Thank you. This was by complete design. Complete design. Especially because my mom just got to the chat, so welcome. I hope the card game went well. And I'm sure it did. I'm sure she won. It's not like a terrible dream or something where you're on a live stream and then you incorporate a bug and then your mom shows up to make fun of you. It's not like that. This was all part of the plan. And yeah, this is actually a great instance of, and I've got a note here, but of course I didn't follow it. A great instance of making sure that you understand short circuiting. So we talked about, here's a teachable moment. We talked about short circuiting before and said, if something, you test multiple conditions and it's an and of those things, and one of them is false, well, you don't need to check the and of the others. So when we look at our functions, I got ahead of myself I wrote a function that was so wrong that it was actually wrong. And that is, when I looked at the order of the tests that I make, ooh, this is a subversive little bug. I look at the order of the tests that I make. I want to make sure that infield is true before I do any of these other things. And if this is not in the field, I do not want to access that. So that was very astute. Thank you for the help from the chat on that. To immediately tell us, we could see the line where this was being caused, but we would need to dig in and test like a lot of test data sets to see exactly what's going on here. And the reason why it's going wrong is that we need to make sure that it is in the field before we access it. That would be bad. So the infield check should happen first. And now when I come back down and I hit the up arrow to run this again, the boards get drawn. So we did have a bug. It was perfectly intentional. I meant to put it there, and teachable moment, blah, blah, blah. And in the meantime, hopefully it's going to work. You know, we're still in the can Philip code decently enough for this to work live. We'll see. But in the meantime, we've almost done the whole thing, except look at how infuriating this is, that it said, I coded the game of life. I read the game, read the board. I played the game of life. I drew them to surface objects. And it's like, where do they live, right? And so we need to be able to see all of these things. So let's see them. Here's where we get to use animate.py. I explained Pygame service to NumPy on our website. It is annoying. It is because we wind up needing what are called NumPy arrays in order to make this conversion to a video. And their axes are swapped with how Pygame is representing this. And so we have to swap the X and Y axes. This goes back to us talking about graphics and saying the graphics coordinates are backwards compared to row and column. So in row and column, you go down and then over. And then in Pygame, you go over and then down. So because of that, you need this function to switch the axes when you do one conversion to another. And then there's a lot of like video processing stuff that's just boring. And all I want you to think about this is, this does not return anything. It takes two inputs, a collection of Pygame surfaces. That's good. This is each one is a snapshot of one generation of the board. And then we have where we want to write this thing to. So all that is good. And it's going to add what we want is like, this is going to write it to an MP4. And we're going to need a little bit of extra imports in order to do this. So I'm going to do that here shortly too. But in the meantime, in the spirit of thinking top down, this is all I care about. I take the surfaces, I take the video path, and I call animate surfaces, and it's going to write it to that file. So let's do that. I'm going to come down here and say animating the game of life. And so I'm going to call animate, I think, from animate. I'm going to need to import that function that I care about, which is animate surfaces. So I'll import that. And now I'm going to call animate surfaces. And I'm going to call it on boards, which are actually in this particular case, not boards, surfaces. And in this particular case, I'm going to say the video path that I care about. Okay, so this is the video path that we had indicated before that I thought I took. It's the output prefix. So the video path is going to be, okay, not quite that. So let's say the video path that we're going to go to is the output prefix, which is a string plus .mp4. Just a minor little thing to add the mp4 file name to the end of it. So now we're going to say we write the surfaces to this particular video path, and that's going to make the video at that particular point, so it will pop up in the output. If we make it here, we can say, okay, we made it, animation finished. And so, hey, I guess we could say, hey, we're going to exit normally because we made it through all of that code. So when we save it and then we run it, we're going to close our eyes and hold on to our butts, in the famous words of Samuel L. Jackson. And we said, okay, that happened very quickly. I'm almost terrified at how fast that happened because, number one, Python is very slow. But hopefully it's going to be the case that the dinner table was just because we implemented it for only 60 generations and it's not that big. Hopefully that was just a fast simulation. So here's where we keep our fingers crossed. And we hope that we see a nice animation. So remember, the dinner table that we saw before was, I added in images, was this oscillator. And that was the previous rendition of this that we had not drawn that showed all of these cells as, you know, squares and they're in a grid form and you have all these lines. So let's see about ours. Okay, the initial state's good. The terrifying thing is when we go initial state and then nothing happens. Appears to be good. Now, we could change the frame rate. Your code might not have worked. Okay, so there's one thing I should have told you before we actually run this. I have a couple things installed behind the scenes. So if yours doesn't work, we need a few things installed from pip. And one of them is Pygame. You can click run on that, but you probably already have that installed if you followed our drawing discussions. We also need NumPy, and so we need to install that too. I happen to have it installed, so everything was okay there. And then we need pip3 install, and here's where you want to install image IO, but you want it with extra dependencies that include this FFmpeg encoder decoder. And so you need FFmpeg in brackets and then close quotation marks. So that installs the extra dependencies there. So you need all three of those things: Pygame, NumPy, and then this image IO FFmpeg. Then we're able to produce these animations. And I can just keep hitting up until I see this. I might make this like 60 or something, just to make a prettier animation, because the animation's only for 60 generations. So now we see the edges get a little bit sharper, and we've got our dinner table. Of course, the dinner table is just an oscillator. At one point in time, this was probably amazing. But what we care about is looking at a couple of other things. So number one, we could look at our glider gun. So in this particular case, I'll just hit up to say I'm still running main.py, but I want to run the Gosper gun as our input, and I wanted the output to go to output/Gosper gun. And I want to run this for, let's see, I think this was the cell width. We could keep it at 60. I'm a little worried. Let's tile it down to like 30. And then let's make this 400. So that's going to run this for 400 generations. And we're going to let it, it's read in the game, the board. Now it's playing the game. So it's doing the process of simulating the boards over multiple generations. So it's not doing any drawing yet. And this is the other nice thing about separating out your task modularly, because you can see the simulation is running. And that's different from doing the visualization. The visualization is about to happen. This will be worth the wait, I think. While we wait, I'll say a couple things. Number one, I just like this visual so much better. I mean, it could be a personal preference thing, but I think this is so much nicer and crisper than what we had before with this sort of crossword puzzly view of the game of life. But that might just be my own preference. Other thing I would say is, what is the Gosper gun? So this is what we're trying to visualize. It's this factory of sorts that produces these 5-cell elements. So the game of life has now been played. Update, it finished. It gives us a little bitty warning about the fact that it has to like resize some of these surfaces. That's very minor. So the boards have been drawn to file. It's animating this, and it should finish here quickly. Usually these MP4 conversions are pretty fast. Nearly there. Looks like it's making the MP4. So it's made the file, but it's not yet added all of the elements. Okay, so now it's finished. Hallelujah, animation done, and we can exit normally. And now we can take a look. So we had the previous version of this Gosper gun. Here's my version with nice little circles as the cells. And we're going to keep this same drawing apparatus when we generalize what we've done to multiple automata. So we're able to represent huge collections of automata. And the history of this particular one, I should say, is this was the first known version of the game of life where the population of cells grew unbounded over time. So you imagine these little gliders are swimming off into infinity. If you have an infinitely big board, the number of alive cells at any point in time is growing without bound. So it's named after Bill Gosper, who was the first person to find such a pattern. And then it's quite an interesting one because it's almost like a factory where they're making these gliders. And that's connected to this notion that we're going to talk about next time of, well, could you make gliders that are like self-replicating? And then they might grow exponentially. But that's a discussion for next time. And then in the meantime, what I should write is, I'm a little hesitant to run this for a huge number of generations because I think we're going to have to wait for the pentomino. So let's see what happens if I dial down the pentomino a little bit. But the boards is going to be, at least in terms of the cell width, I don't want it to take forever to render. The boards are going to be pentomino.csv, and the output is going to be pentomino. And to really look at this thing, we need to see it for a lot of generations. So we need like 1,000 plus generations. So I'm going to run it for those parameters. And I'll stick around. So we will wait on it to finish. I don't think it'll be too bad. I think it's just going to take a few minutes. Let me know if you have questions in the chat in the meantime, because I would like to see our visual of pentomino. Astor has a good question in the meantime. Can you back up the truck, interesting analogy, and run the game of life backwards? So inverting the game of life, meaning going from a current state to say, what did this thing look like 100 generations ago, is a really hard problem. I think it's like provably NP complete. And so the issue is, the reason why that is that, well, much like real life, it's hard to know exactly how it is that we got to this particular configuration of anything, right? For example, like genomes, the collection of DNA of all organisms. Like, we're not necessarily able to reverse engineer all the mutations that got us there. Game of life is even trickier because you could have a certain board that actually doesn't come from any predecessor 100 generations ago. Like, there's no possible way of getting to it. That's one thing that might make things hard. Or there might be multiple alternatives. And there's a certain structure with an automaton like this, but a lot of the ones that we're going to look at are not going to have this beautiful linear glider factory structure to them. So if your question was, in the case of the gliders, we could maybe force them back into the factory and do it that way because you have all these independent little sub automata. But real automata have like all this explosion of communication almost across different cells. And that's easy to implement forward, but it's very, very challenging to implement backward. I remember I saw a talk about this. Martin Gardner was a famous popularizer of math and science concepts by writing many, many books and so forth. And there was a conference, I think they might still hold it, but they held it in his honor every 2 years. And then he died and they kept holding it for a few sessions. And the idea of the conference, first off, it's a cool concept for a conference because regardless of how prominent the speaker is, you would get, I think, a max of 15 minutes. Most speakers would get 5 or 10 minutes. I actually saw John Conway talk at the conference, and they gave him 25 minutes, and he's like quite famous because he was the popularizer / inventor of this particular automaton. So everybody wanted to see him. But even still, they only gave him like a 25-minute slot. Most people had 5-10. And one of the talks I saw was inverting the game of life. So all these talks were just like people who just loved some of the weirdest little things in math. But the talk on inverting the game of life was really neat because it's such a hard problem. And the person was talking about all of I think that the time there was like a 14-year-old kid gave the talk, but they were like very, very, very smart. And they'd come up with some algorithm that, no one had ever come up with an algorithm this fast for trying to invert the process. Still waiting. I seem to remember it takes like 4 or 5 minutes. So we'll get there. There is another meta comment, which is what we are seeing. Oh, ooh, the boards got drawn. So the boards got drawn fast. This is not going to be the highest resolution picture that we're going to see. Oh, it's done. Okay, so that's because I set the cell width to 5. Now this might be kind of ugly, but we're going to take a look anyway. And if you want it to be not ugly, just get your code to work. Let us know, like on the Discord or something, if there's some issue that you encounter. And we're happy to help. But raise the cell width parameter and just be willing to wait a couple extra minutes because it'll be that much prettier. So here's our pentomino. When we click it, and that's enough resolution for us to see. We start with just 5 cells, but you get all of this like frenetic communication. And what's really cool about it is you see one glider start to go off into the distance, and now 2 more and 3 more emerge from this madness with all this communication back and forth. And now we see a 5th glider that gets ejected from it. Parts of it have become stable. So these are 6-cell or 4-cell stable forms that are never actually going to change unless something comes in and collides with them. And yet you still have all these generations. There was a glider that tried to form and then it hit the center of the factory. And you continue seeing all this. It seems like it's calming down. You have these little oscillators here over beneath the main pattern of activity. There's no real rhyme or reason to any of this. Like no one, who on earth would have predicted that this is the behavior that you would eventually see? And you can see why this became famous. And then you wonder, is it ever going to stop? We made it just big enough to capture all of the different cells. And then look at this. You get at the very end of all of that, you get 2 more gliders that get formed and ejected out into outer space. I think that's one of the most fascinating parts of all of this is that you get like these random gliders that just happen at the very end. And then as a result of this, that glider will go off to infinity and join all of its other friends exploring the outer reaches. And meanwhile, you get stability in the middle and you get some of these alternating patterns. Now, some of this stuff on the boundary, it's because when the gliders hit the boundary and like collided with the edge, we didn't handle exactly what to do on these external edges. And so we wind up with these forms because when the glider is going out there, we're not keeping track of that. Actually, technically, like this cell off the board is alive. And so that creates a little bitty bug. So what we have is not 100% perfect, but I think you'll acknowledge it's pretty neat. My point is, our work is not done. So I've loved the game of life since the first time I saw it, but we're going to do something much more ambitious. And I'll explain why we're going to do that. But number one, remember, if I can do something once, I can do something n times. And by the same reasoning, if I can implement one thing that is neat, maybe we can implement all things that are neat. So next time what I want to do is implement all cellular automata. And the reason why is that this is an example. The game of life is an example of something that gets popularized, but then in the midst of it being popularized, people fall in love with the popularization, and everybody forgets why anybody cared about cellular automata in the first place. And the reason why they cared about cellular automata in the first place was von Neumann's question, going back to like the 50s, of is it possible to build a system that shows the ability to self-replicate? If we look at something like the Gosper gun, this is the replication of gliders in the same way that like a car factory is the replication of cars. At every point in time, there is, or for any unit of time, there's a fixed number of gliders that get manufactured. What von Neumann was interested in at the foundation of the entire field of cellular automata to begin with is it possible to make a pattern that self-replicates and allows this system to grow exponentially? So you might imagine if we made space probes that worked like that, they could explore the outer reaches of the Milky Way. And also when they find new resources, they could multiply. And so you get exponentially growing probes that are called von Neumann probes in his honor. Everybody always forgets that that's what he was trying to study. We've got a lot about this in terms of background reading on Programming for Lovers website. Next time, what we're going to see is, can we build a self-replicating automaton? The hint is, yes, we can, and it's amazingly beautiful. But in the process, can we build something that will simulate all automata and then be able to look at a bunch of them that all have different properties? That might sound like a lot, but if we can do game of life, we can actually do all of that. That having been said, it's all for next time. I'll see you then. And in the meantime, happy coding.